So looking at pKa's, we can look at some of our periodic trends. And one of the things that we determine using the periodic table is the electronegativity of atoms. And we know that electronegativity increases moving to the right and moving up. So that fluorine is the most electronegative atom. And when we consider electronegativity, we typically ignore the noble gases. So, knowing the rules that in electronegativity increases as you move to the right, we know that carbon is less electronegative than nitrogen, nitrogen is less electronegative than oxygen, and oxygen is less electronegative than fluorine. When we compare atoms of the same size, meaning same row, typically, the strongest acid has its hydrogen attached to the most electronegative atom. So that means that acidity increases in correspondence with electronegativity of atoms of the same size. And atoms of the same size typically exist if they are in the same row. So you could also, because you will always have access to the periodic table, look at the electronegativity of atoms in a same row to decide which atom, when bonded to fluorine, will be the strongest acid. And the reason that it will be the strongest acid is because it will have the largest dipole moment. And that means that fluorine is pulling the electrons away from hydrogen more effectively, and that means the bond is weaker. So that means weaker bond. Okay, so we can also say that the strongest acid has the weakest bond to hydrogen. So acidity increases across a row as you get to the end, to the right. And we can compare, knowing these rules, we can compare alcohols and amines. Alcohol, the oxygen is pKa of, so the stronger acid, the weaker the base. And we know that we can look at the pKa and say, well, the alcohol is the stronger acid, but why is it the stronger acid? Because oxygen is more electronegative than nitrogen, because oxygen is further to the right on the periodic table, which goes, just looking at the right-hand side, boron, carbon, nitrogen, oxygen, fluorine, right? So that's the order So that means that oxygen is more electronegative than the nitrogen and should make a stronger acid. And you know I like the abbreviation EN for electronegativity. Why are protonated alcohols stronger acids than protonated amines? For the same reason. But notice we're only comparing molecules of a similar structure. The only difference between the two molecules being compared is the electronegative atom O or the electronegative atom N. We are not changing the number of carbons or hydrogens. Okay, we might change the number of hydrogens. So we're comparing OH2 to NH3. But needless to say, they have the same basic difference because they each have one extra proton, not 2 or 3 extra protons. So a protonated alcohol is more electronegative than an amine. And that is why the pKa is lower than that of a protonated amine. More acidic. And you can take all these little rules that you learn and use them to help you determine and rank molecules according to their acidity or basicity. Another characteristic that we can look at in looking at pKa is the hybridization. When you use hybridization to look at the effects of electronegativity and determine acidity, you can only compare molecules that differ by the number of pi bonds, not by the atom that is bonded to the acidic proton under consideration. So we can compare CH that has a triple bond, a CH2 that has a double bond, to a CH3 that has a single bond, but we cannot compare using hybridization an NH group to a CH group. We can only compare CHs to CHs when we consider hybridization. And so we can say that when we are comparing in this way, as the percentage of S increases, the electronegativity increases, and that as the percentage of S increases, then the acidity increases. So for sp, there are 2 orbitals in total, and one of them is S. So we can write this as 1s out of 2 total, and that is 50%. sp2, we have 1s out of 3 total orbitals, and that is 33%. And then for sp3, we have 1s out of 4 total, and that gives us 25% S. So when we compare the carbon to hydrogen bond for acidity, and we know that the carbon to hydrogen bond is from an sp carbon to an S hydrogen, that this bond sp to S has a higher S percentage than an sp2 to s bond for an double bond, carbon to hydrogen, and that when we only have single bonds, the carbon to hydrogen bond is from an sp3 to s orbital, and that the amount of s character in an sps orbital is greater than the amount of s character in an sp2 to s, which is greater than the amount of s character in an sp3 to s. So that we have 2s out of 3 total orbitals for the triple bond, and 2s out of 3 total, and 2s out of 4 total for the double bond, and 2s out of 5 total for the single bond. So we have 2/3 s to 1/2 s to 2/5 s character, comparing the triple bond to the double bond to the single bond. And 2/3 is like 66.67%, and 1/2 is 50%, and 2/5 is 40%. S character. So the strongest acid has the highest percentage of S in the carbon to hydrogen bond, and is also the most electronegative carbon to hydrogen bond. Okay. I don't like this slide. I'm going to delete this slide. Keep, then delete. Size effects and pKa values. So as size increases down a group, right, we can compare size across a row, but the difference in size is much smaller than a comparison of size down a group. And so as we go down a group, size increases a lot, and the bond becomes longer, and a longer bond is also a weaker bond. So down group, longer and weaker bond. But I said, give me the pen. Yes, okay. Down group, and in this case, we're looking at group 7, halides. Longer and weaker bonds. And we said that acidity can be determined or correlated to the stronger the acid, the weaker the bond to hydrogen. So if you know that bonds become weaker as you go down a group, you would expect the largest to have the weakest bond, and the one with the weakest bond is the strongest acid. So in this case, the largest ion, iodide, makes the strongest acid with hydrogen. When atoms differ in size, so down a group, the strongest acid has its hydrogen bonded to the largest atom, and it has the weakest bond. Weakest, longest bond. And the reason that the bond is longer is because, and weaker, is because it's further away. The electrons involved in the bond are in the outermost valence shell, and as the atom gets larger, the outermost shell is further and further from the nucleus, and so the attraction to the nucleus is weaker, and the bond is longer, and that makes it less stable and more reactive. Some more pKa values to remember, and these are in the chart that I gave you already. pKa's of the halo acids. I actually did not put those in the chart, I just said that they were strong acids. Except for HF, which is pKa of 3, which is considered a weak acid because moderately strong acids have a pKa of 1 to 3. Okay. Then water, we talked about that, 16. New one, H2S or thiol, pKa of 7. If you want to name this like you name as you name non-metal molecules, then you should remember to call it dihydrogen sulfide. Now we have ammonia, pKa of 36, and the alkane, pKa of 60. Those are things that we've already discussed. Okay. I should have just erased all the writing before you. Acidic proton is not bonded to hydrogen. Size of the hydrogen proton. Okay. It will be more clear if I say this separately. I'm going to erase everything, and we'll pick this up on the next video.